So this one is pages 129 through 148 in our book. So if you have not already gotten that out, go ahead and tear those pages out, please. So this lesson, we are actually going to be looking to see what would make the representation change, but the numbers are the same. So we're looking at multiple representations of the same thing. So to start off with, I want you to pause it, and I want you to answer 1 and 3 on this page. So 1 is 7n times 3n plus 1. To answer it, you had to distribute, giving you 21n squared plus 7n. On number 3, we're not going to worry about this one just yet. For number 3, that's where you multiply from the outside in. So 4w and the 2, and 4w and 2. 4w times 4w is 16w squared. 2 times 4w is 8w. 4w times 2 is 8w. And then we end up with 4. And so when we add those together and combine like terms, we have 16w squared plus 16w plus 4. And that would be your answer. So for this one, I want you to look and see which one is the odd one out. And can you tell me why you think it's the odd one out? If you chose relationship A, you're correct. It's the only one that's not a function. If you chose relationship B, it's the only one with a changing rate of change, so you're right. If you chose relationship C, it's the only one with a decreasing value as you're going left to right. And so it is, and it's linear. So this one is quadratic because it's a steadily changing rate of change. This one's linear. D is the only one with discrete data because you can't have partial apps. And it's an exponential. Because it's doubling each time. The special name for A is the conics. And it is more specifically a circle. And the way you write the formula for a circle is x squared plus y squared equals your radius squared when the circle is at the origin. And so in our case, our radius is 4, so 4 squared is 16. So this would be the equation for that conic. And things that tell me that this is not a function is there's a y squared, and if you have a y squared, it's not going to be a function. And if it doesn't pass the vertical line test, meaning I draw a vertical line, am I going to touch 2 different y values? If the answer is yes, then it's not a function. Now, if you'll flip to the back of this section, you'll notice that there are some cards to sort. This is to go with the next section. And your goal is to take these 6 graphs and match all the information that goes with them. There will be between 3 to 5 cards in each section. And so you're going to sort it between those, and you'll put those between those 6 different places, and you'll put those 3 to 5 cards grouped together and glue it to a paper. Now you're done with those, we're going to actually talk about how did you group your representation into groups? Well, did you take the data in the table and plot? Did you take the fact that the graph was upside down and look for the negatives? Did you use your graphing calculator? Did you identify that you had a linear and an exponential and pull those out? Oh, and a conic? And take these three out of the running so you didn't have to worry about those. Those are all different things you could have done. How did you know which relationships were functions and which ones are not functions? Well, we'll talk about this as we go through the next bit. And we're going to look at the graph, the table, and the equation. And then how can we identify the function family associated with each grouping? So as we go through each set, we're going to answer that question. So these two are going to be answered as we go through each of the pages. So you can write it on here, or you can write it on the pages where you have your notes. So the first set I pulled together. We have the parabola that's facing upside down, which tells me it's going to be negative. If I take these points and plot them, -4, and then I go down to -1. Oh, thanks. Yeah, -1, because we're counting by 2's on the y. -3, 0. -2, -1. -1, -4, and 0, -9. Those are all plotted. And then you could have graphed these in your graphing calculator to see the image that you have and see that those match up with your graph. And the wording here, axis of symmetry, that means that we have folded over the line x equals -3. The vertex is at a maximum, that means it's the highest point. And the graph opens down. That all fits. So which function family is this? It is quadratic. And I can tell that because I have a squared x term. When I multiply this out, it'll be a squared x term. My parabola is shown, so that means it makes that u. And then I don't have that consistent rate of change. So I've increased by 1, decreased by 1, decreased by 3, decreased by 5. And so you see we're constantly changing it, going one way or the other. So this one increased by 2 to get there. This one increased by my rate of change changed by 2 each time. And if you look here, that was also a change of 2. And so that's a quadratic. Here's another example of a quadratic. This time our vertex was at -1, 4. And so as I look and plot the points, so that's this first point, -2 is at 5, -3 is at 8, 0 was at 5, and 1 is at 8. So that checks out all those numbers. And then when I plug this in my calculator and I see the graph, it's going to match up here. So again, we have the squared term here. We have that rate of change. So here we had a decrease of 3, decrease of 1, increase of 1, increase of 3. And so we changed by 2, we changed by 2, we changed by 2. And so that second change is always 2. And so that means it's quadratic. This next one doesn't have that u. It is growing steadily as we go, or growing faster and faster as the higher up we go. And so that's an exponential. We look at it. To get to the next one, I'd times 2, times 2, times 2, and times 2. That means I have a constant multiplier, which is an exponential. When I write something with a constant multiplier, that means my exponent is my x. And we have 2 people the next day, and they each tell 2 people more the following day. And so each go on to tell 2 new people the remember each day. And so that will be exponential. And then the linear one. This is linear because we have a straight line. There is no exponents on your variable. Nothing else being done to your variable besides multiplication or addition. We add 2 new people that hear about the secret each day. So we're increasing by 2 each time. And here we're increasing by 2 each time. And if I plot the points, these will plot up here. And so those are all ways to tell it's linear. So the rate of change for the first change is consistent. This next one is a conic, more specifically a circle, with a radius of 2. And so I come over here and look at the graph. I have the radius of 2. Come over here and I see I have 2 negative 1s that point to any of my y values. That means this is not a function. So far, everything else has been a function. But this one fails that vertical line test. And then I can also see it here because there's 2 different y values for that negative 1. And I can see it here because there's a y squared. So those are all ways to tell if it's a function or not a function. And it is a conic. Now we have another parabola. This time our vertex is at -3 and -4. And if I look here, I'm like, okay, my rate of change is -3. Wait a minute, I skipped a lot for my x, so I can't check this next rate of change. Let's look at the next one. I added 7 and I added 9, so this one has a difference of 2. I can't do anything really with this one because I didn't have that next steps of your rate of change. And so this is a quadratic. Because my second steps are the same rate of change. I can also tell from my equation that is squared. And this is the 3 different main representatives we'll be using. This is your standard form. This is factored form. And this is vertex form. So those are your 3 main representations of quadratic. Oh, I was writing undo. Wrote quadratic and function in the same word. Sorry, quadratic function. So now we're going to be looking at equivalents. We're going to look at equivalent functions. We're going to sit there and I want you to look at this tile design and see which various patterns you can notice. And then we're going to come up with patterns for those. So we're going to kind of do this all together on number 2, but this is answering 1, 2, and 3. And so we're going to focus in on the white, the gray, and the total number of tiles. You really could have done this chart in any way. And so you're going to find that I want you to go ahead and count and fill in this portion of your chart. So for your white tiles, you have 12, 40, 84. For your gray tiles, 13, 41, 85. And your total number of tiles, 25, 81, 169. So let's go ahead and focus in on this page. We're going to focus in on the white. And let's look and see if we can find a pattern. So I'm just going to take and look. I look like I have these 4 different ones that all match. And it seems like it's consistently 4 that match on all of them. So I need to figure out what is going on with each of those spots. Well, here is a 1 by 3. Here it was a 2 by 5. Here it was a 3 by 7. And so if I was to predict on design number 4, it would be a 4 by 9. This first number always seems to match your design number. So we can call that, it wants us to do it in terms of n, so we can call that n. Now let's figure out how we get to this 3. Well, I had 3 here, and I had 5 here, so I increased it by 2. I had 7 here, so I increased it by 2. And I have 9 here, so I increased it by 2. So this is a very linear pattern for that number. I have a constant increase of 2, so that means it's 2n. And so let's check it. 1 times 2 is, we're taking that design number, 1 times 2 is 2, plus 1 gives us a 3. So let's check and see if 2n plus 1 will give me 5. So I'm plugging in the 2. So 2 times 2 plus 1, that does equal 5. Let's check it over here. 2 times 3 plus 1, that equals the 7. And so that works consistently. Well, that's what gives me one of those spots. I need to have all 4 of them totaled together. So that means I need to have 4 of those n times n, 2n plus 1. And so now I want you to go ahead and see if you can figure out the white tiles for 4, 7, and 10. You should have gotten 144, 420, and 840. We're plugging that into that formula. So now let's look at the gray. We're going to focus in on that gray tiles. Well, I have 2 different types. I have this center part, I'm going to call that big. And I have these little small ones. I have 4 of those small ones. Well, how do we come up with that small area? Well, if I have to look at my design number, this is a 1 by 1. This is a 2 by 2, 3 by 3. It looks like that is design squared, so n squared. N squared. And I had 4 of those, so 4n squared. So now let's look at the big ones. So for that big area, it is, for that first one, I'm just going to write it down, 3 by 3. The next one was a 5 by 5. For the next one, we had a 7 by 7. And so some of you may have already noticed this is the same pattern that we had the previous one of how we increase. So we're increasing by 2 each time. So that means we have 2n, and we need to add that 1 to get there. Well, that's going to be the same for both of them. So I can just put that as squared. And now let's use this to help you find your 4, 7, and 10 gray tiles. wait, you may have noticed something else here. It was always increased by 1. So if you had, instead of doing this formula, had used your previous formula, and then added 1 to it, you were correct as well. So that is 2 different ways you could have come up with the same formula. So now we're going to look at the total number of tiles. So if I come over here, I see that these are each squares. And the area of a square is going to be whatever my side is squared. Well, what's my side? In this case, I have 5. And in this one, I have 9. Here, I have 13. This time I'm not increasing by 2 each time. I'm actually increasing by 4. So it's going to be 4n. And then what do I need to add to that 4n? So 4 times 1 plus what is 5? Okay, that gives me plus 1. Okay, 4 times 2 is 8, plus 1 is 9. So that area is 4n plus 1, that quantity squared. And go ahead and find 4, 7, and 10's totals. So you should have come up with, 289, 841, and 1681 as your numbers. Another way you could have come up with the equation, you could have added these 2 things, and that would give you this equation. So this equation could be multiple different things, but it will all simplify down the same way. So when you're looking at how many tiles were in design 7, you plugged in the 7 and you found out those. But let's take this next one. We already knew it was 10 because of the way the chart was set up. But how can we take and figure out from this number to go back and find the design number? Well, I know this is the area of my design. And so if I take the square root of it, that's going to give me 41 point something. So that means each side is 41 long. How can I figure out what it is? Well, we know 2n plus 1, not 2n, 4n plus 1 gives me my pattern number. Subtract the 1, divide by that 4, and then that would give me design 10 is the one I'd be wanting to plug it in. We've already done 6 by what we did on the chart. So let's take Tanya and Alex. They came with different expressions to represent the gray tiles in each pattern. Their expressions are shown. Are they any different? Basically is what the question is. Tanya says there's no way, or Alex says there's no way, and Tanya says that they are. So let's look at it. So for Tanya, we need to figure out what this is. So let's multiply 2n plus 1, 2n plus 1. 4n squared, 2n, 2n, 1. And then for Alex, actually, let's go ahead and finish up Tanya's. So we have 4n squared plus, and this would combine down to 4n squared plus 4n plus 1. When I combine like terms, I get 8n squared plus 4n plus 1. Now let's do Alex. And we have 4n and a 1, 4n and a 1. So that gives me 16n squared, 4n, 4n, and 1. So this would combine to give me 16n squared plus 8n plus 1. Now I need to take Alex and take that negative 4n and distribute to both parts. So that's the second part of it. So negative 4 times positive 2 gives me a negative 8. N times n is n squared. Negative 4 times positive 1 gives me a minus 4n. Combine like terms gives me 8n squared plus 4n plus 1. So these two expressions are equivalent, then they are the same. So let's take the same idea, and we're going to be looking at the white and the gray tiles added together. Does that equal the same as the total? And so we said the white was 4n times 2n plus 1. Our gray was 2n plus 1 squared plus 4n squared. And so we need to figure out the multiplication of this. So 4n times 2n gives me 8n squared. 4n plus 1 gives me 4n. Now when I square that, I have 2n and 1, 2n, 1. That gives me the 4n squared, 2n, 2n, 1. So plus 4n squared plus 4n plus 1 plus 4n squared. So when I combine together all my squareds, I come up with 16n squared. When I combine together all my linear terms, I get 8n. When I combine together all my constants, I get plus 1. Now for our total, we had 4n plus 1 squared. So this means I'm going to go to that chart, the box, and do 4n and 1, and fill it in. 16n squared, 4n, 4n, and 1. So that gives me 16n squared plus 8n plus 1. So these are equivalent. So now let's look at the function families that describe the patterns for each of the, so we had quadratic for each of the white tiles. Same thing for our gray tiles. And when we added the white and gray tiles, it still belonged to a quadratic family. So always, sometimes, or never to complete each statement. Two functions are always, sometimes, or never equivalent if their algebraic representations are the same. So if their expressions are the same, then their functions are always equivalent. Two functions are always, sometimes, or never equivalent if they produce the same output for a specific input value. And that one is sometimes. Oh, that caught on me as I was writing. Two functions are sometimes, always, or never equivalent if their graphic representations are the same. So if the graph looks exactly the same, then it's always. Determine if each table values is a function. If so, identify the function family. So let's look and see. From negative 13 to 12, we increased by 1. From 12 to negative 8, we increased by 4. From -8 to -7, we increased by 1. Oh, wait a minute, there was a break here, so I really can't compare these. And from -7 to 3, increased by 4. And so we have a non-steady rate of change that does become a consistent rate. And so, therefore, this is a quadratic, and it is a function. Let's look at this next one. -2 to 0, we increased by 2. 0 to 4. Ooh, on this last one, I didn't catch it. There were actually multiple times where my rate of change did not stay the same. So let's look at it. We increased by 1. And then go all the way up to 5. We increased up here by 4. And so there were 4 movements between this. So we're really just increasing by 1 each time, linear. So be careful on these x values. These sometimes cause you problems. Another thing you can do is you can do -13 over 5 and see if your rate of change, -13 over 5. You do your -13 minus a -12 over -5 minus 4 and see if that rate of change stays the same, and it does. This time we are being consistent by not, so some of them are increasing consistently and some of them aren't. So like here, we start by increasing in this next section consistently. So to go from 4 to 18, we increased by 14. Go from 18 to 40, we increased by 22. So our rate of change is not the same. But if I was to go out to the next change, which this is a difference of 2, so here's another difference of 2. And so that one was by increased by 2. And so you'll look and see that we have constantly been changing out here, and we'll have the next change is going to be consistent. On this next one, so this is quadratic. All our 4s are going to different y values. This is not a function. And it is a vertical line. Determine if these function pairs are equivalent or not equivalent. And so you have to do the math out for these sets. And so we're going to try to simplify that first line to see if it looks like the second line. X and 4, x and 4. So x squared, 4x, 4x, and 16. And so that's what it's going to be right here. So I'm going to do x squared plus 8x plus 16. I still need to bring down that plus 6 at the end. 16 plus 6 gives me 22. So 8x, or x squared plus 8x plus 22. And that does match, so these are equivalent. And because there's that squared, that means this is quadratic. So in this next one, we have to do a little bit extra work because they have 2 sets of things that we need to take care of. And so this x plus 1 first. So that gives you x squared, 1x, 1x, and 1. And so when I combine like terms, I get x squared plus 2x plus 1 plus 2x squared. And so when I combine like terms, I end up with 3x squared plus 2x plus 1. So I want to see, is that equivalent to this next one? And this next one, we need to take into a box for that first part. We have 2x and 1, 2x and 1. Gives you 4x squared, 2x, 2x, and 1. And so when I combine like terms, I have 4x squared plus 4x plus 1 minus 2x times x plus 1 is equal to that second function. So in this one, I need to take that negative 2x through to both pieces. So negative 2x times x gives me negative 2x squared. Negative 2x times 1 gives me a negative 2x. And when I combine like terms, I end up with 2x squared plus 2x plus 1. And these are not equivalent. And we'll be working on the other part of the assignment later.